Welcome to the Rise Up Podcast, Episode 6. This episode, as well as the next, will be continuations of the same conversation, so we're going to go ahead and jump right into it. Thanks for watching.
So, let's revisit some of the topics we visited from the UNS. So just as you described it, there's a lot going on with the manufacturing data hub, but it's just to ensure that there's good fidelity of the data. It's, once somebody needs to consume it, because I think that's really the value we're trying to create here is, getting data in a database is not hard. Collecting data is not necessarily hard. It's always my ability to ask the data questions and to get actionable stuff out. So there's a lot that goes into that. But you mentioned a word, orchestrate. And Geoff, I want to talk a little bit about this as a topic we talked earlier in the UNS is this idea of orchestration versus choreography. And, to me, orchestration it would suggest that, if I'm the conductor of an orchestra, I'm going to be that central point, that anything that occurs when it's time for the violins to play, I'm going to bring the violins in, or when it's time for another, part of the, orchestra section, they need to do something different. I'm going to orchestrate that. And of course, it means that there's the conductor who's involved in all aspects of what's happening with an orchestra, versus choreography. And we think of this in terms of dance is, the violins in this case are going to do something based on what, say, the cellos just did, but there's really no method to ensure that occurs. So, when you talk about these concepts, orchestration versus choreography, what does that mean within the context of the manufacturing data hub?
Yeah, it's a good question. So what it means is two different approaches to how logic happens. And it's best demonstrated with an example. So if I go back to the car that I was talking about, and this scenario of monitoring the engine temperature, and I want to have a service, some code somewhere that listens for the engine temperature going above some sort of limit, and books my car into the mechanic if that happens. Probably says something about how old my car is that I'm thinking about this. So if we think about that example, we've got telemetry, we've got some rules about temperature going above a set point, and we've got some function that's doing something about it. In choreography, what that means is that all of that's really in one service. So one bit of code is deciding what it's going to listen to, what the rules are for what it should do about it, and then going and doing the thing. And maybe doing that thing is publishing some other event that some other service is going to be listening to do its thing. So I might have two different bits of code, one listening to the temperature and detecting, the alarm condition and publishing an alarm. And then I might have another bit of code that's listening to the alarm and, doing its thing of saying, well, okay, when that alarm happens, I need to book the car in for a service. But the logic of the subscription, what I need to listen to, sits with the code that's taking the action. Mm-hmm. That's choreography. Orchestration, which you said is the conductor out the front, separates those two things out. The subscription, listening to the event, is separate from taking the action. So, we publish an event, but there's a central orchestrator that's saying when this event occurs, that action should happen, but the action is not part of the logic that's saying, when this event occurs, that action should happen. Those rules are separate from taking the action. Now, why is that important? What difference does it make? Well, both approaches can get you a system that books your car in for a service when the engine gets too hot. But there's very different impacts of the two. So, the first, the choreography approach, where you've got these two systems, they're logically decoupled, right? They're kind of separate systems, and they're both listening to their own events. determining what they're going to do and then go and do it. It's very difficult to trace through from one end to the other what happened from the temperature in the car through to booking the service. In a simple example like I've just given, you can probably look at the logs and look at the events and figure out what happened. But let's say you've got hundreds of different services doing very complex stuff. It's very difficult to trace through from one end to the other what happened here. And if something goes wrong, it's very difficult to figure out why it went wrong. So the bigger you build a system like that, the more brittle it becomes when you're relying on a completely decoupled service, working with a contract, and you can't really know what the impact of changing that is going to be across all of the other services in your system. An orchestration pattern decouples what should happen from going and doing it. But because you've got this conductor out the front who's got the full picture of joining the dots across all the services, you've got a central place to look, trace, create the paper trail, if you like, of okay, the temperature did go high. That created an event. The event came to the orchestrator. The orchestrator said, okay, that temperature went high. We need to now book the car in for a service. So I'll call that service that goes and does that action. And so you've got the end-to-end thread, if you like. Don't want to use digital thread, but it's kind of that concept of what happened, then what action was taken, what event did that result in, and then what happened in response to that event. So I can see the end-to-end process.
Sure.
That's essentially the difference between choreography and orchestration.
Yeah, so it's I guess what I'm getting at here is it's not necessarily a good versus bad. It's that they are two different ways of accomplishing the same thing, but we want to be mindful of what is the impact. So for instance, in orchestration, it might require more services, it might require a little bit heavier of a system, but it ensures delivery. For example, versus choreography, it separates out, it decouples. It has lighter overhead or less overhead, or potentially could. So they're both could be applied. Just I think the important thing here is to understand when to use one versus the other.
Absolutely, and so much of what everybody does in manufacturing is pattern based, right? We see a problem. There's probably somebody's seen that problem before. There's already a couple of different relevant patterns on how that can be solved. And our role as architects is kind of saying, well, what's the relevant pattern that could be applied to this problem, and when should I choose one and not the other one?
Sure. Perfect. So, thinking of some design considerations on that, Andy, another topic we talked about within the unified namespace conversation we had was this idea of composability versus inheritance. And even though these are generally more attributed to when you're doing programming, I think it's important here to understand around, say, data models. So inheritance, say I want to model a pump, and I'm going to create I'm going to call my base pump or my core pump, and then I'm going to build all my other pumps off of it. So maybe I'll have a standard pump, I'll have a complex pump, or there's something along those, but they're all going to inherit from that core value. And the benefit is that if I need to make a change to that pump core, then the others will inherit that. Versus composability, where all my pumps are going to stand alone, and it gives me a lot of flexibility in what is the data, what does that data model look like. And this to me, I think, becomes another important design consideration. Where we landed is absolutely use composability, make sure that all your data models can stand on their own, and I think that's a general rule of thumb. But maybe there can be in times where we want to use inheritance. So again, like I asked Geoff, what does this mean in terms of the context of a manufacturing data hub? How do we apply these two contexts in there?
Okay, so a couple of quite abstract concepts there, composability versus inheritance. To try and bring a kind of a concrete example to this is, within ISO 95, you within the equipment hierarchies, as it were. We've got a couple of key ways to expose how equipment is configured and composed, and what properties they have, and that kind of thing. So ISO 95 allows for equipment, which are equipment instances effectively, and equipment classes, and that the equipment classes themselves define what properties and what attributes certain types of equipment should have. And in the equipment class hierarchy, what we do is we build a hierarchy of objects. So it may be that we've got an object of type, pharmaceutical vessel, for example, and this object type might have it might have a volume attribute, and then a little bit further down the chain, we might have a pharmaceutical vessel, but this pharmaceutical vessel is a fermentation tank. So it would inherit properties from the parent. It would have a volume, but it would also have a valve. There might be a valve, a dump valve on there, or something like that, that allows you to move the material to the next part of the process. So we've got the fermentation. So any equipment instance that is defined as a type of fermentation vessel would automatically inherit the properties of the pharmaceutical vessel and the fermentation vessel. So it would the equipment instance would have two properties on there that have been inherited via the equipment class hierarchy. And when we consider properties of equipment, what we do in Rhize is we look at the class that has been implemented, and we work up the hierarchy and collect all the attributes from the parents, grandparents, great-grandparents of that particular piece of equipment, of those particular equipment classes, and we apply those to the instance. And what something we also support is multiple inheritance. So an equipment can inherit from the fermentation vessel class, but it could also inherit from an equipment type which was OEE capable, for example, or something like that, which would lend it a bunch more properties. So we've got that inheritance properties and methods and that kind of thing, that when this object, this equipment, this actual instance of equipment is instantiated, it inherits all of these properties. So there's an element of composition in there as well, because we've got this multiple inheritance, which means we can inherit from different classes. But the composition side of this also we need to look at how we organize objects within a structure, within a hierarchy. So where if you look at an inheritance hierarchy as being a ISA hierarchy, so this equipment is a fermentation vessel. What you would also want to do is understand what equipment is contained within other equipment, and this comes back to sort of the classic way of looking at equipment hierarchies. That we've got enterprise site area line, and we've got equipment that contains other pieces of equipment. So we might have a production line that has a fermentation vessel and has a heating vessel and has a different type of vessel. I'm not sure what that might be. So we're building not only an inheritance hierarchy on one side that brings properties to an individual piece, but the composition hierarchy allows us to set up parents and siblings in terms of position and containment within there. So that's probably, those are probably the two key areas that I'd probably want to bring to life. We've also got an inversion of that composition hierarchy when we need it, where if you've got for example, if you've got a hierarchy of vehicles, and you've got in the BMW range of vehicles, you might have a 3 Series, and you might have a 5 Series, and you might have an X5 or something like that. those would all inherit properties from the upper class, for example, which might be that these are all cars and they all have doors and they all have wheels and that kind of thing. But contained within, BMW 3 Series would be an engine, and that engine would have properties of its own. It may have there may be an engine speed, for example, an RPM on there. So you would want to look at the relationship between the car and the engine and understand whether inheritance goes up or down in that instance. So the engine wouldn't inherit the properties of the car, even though it is a subclass of the car. It's contained within the car itself. It's not got four wheels, but you could say about the car that the car does have, if the RPM is at 3,000 on the engine, then you could actually say that the car has an RPM of 3,000. So we've got this kind of inheritance on the way down, and also the sort of pushing of property values upwards to parent objects. And then we've also got this idea that objects can contain other objects. And again, it starts to become abstract. And what you end up doing, if you're in a project and you're trying to solve problems and try and understand how objects are interacting with each other and how you need to place this data that's coming in from the shop floor, then you need more than just one tool to be able to do that. To be able to express yourself in a correct way, you do need to have a composition hierarchy. You need to have a top-down inheritance hierarchy. You need to have the inverted inheritance hierarchy. And you probably also need to be able to express relationships between objects that are more like a network than a specific hierarchy. So I think that that general domain and those discussions, certainly ISO 95, allows you to sort of explore this problem domain with a kind of a richness of tools that allows you to sort of arrive at a solution that's sophisticated enough to really represent what you've got. And yeah, as you say, two key tenets of that are composability versus inheritance. That's kind of a starting point for how you would want to think about how these objects are related. And that's just the equipment hierarchy. If you start talking about recipes and process segments and that kind of thing, you get this other sort of, you get a repeating network effect. But actually, indeed, the patterns are the same. I think you just need the vocabulary there to be able to sort of deal with that and further the discussion.
Excellent. Yeah.
And when you're talking
ahead,
about properties, so we're talking about equipment properties there, whether it's the car with the engine and 3,000 RPM, that's a property of the car, property of the engine. When you start to think about, I'm going back to the Uber broker functions here that Rick Bellotta was talking about, in my Uber broker, I need to be able to do stuff. So when you talk about behavior of things as well as the properties of things, that's where it starts to get really interesting with the composability versus the inheritance. So if I look at the engine and I say, I want this engine to have the behavior of over temperature automatically books it in for a service, I need to be able to place that behavior on that piece of equipment. But not all engines might have that. Maybe it's an optional behavior that I want to put in. So it does add this sort of extra layer of sophistication to the requirements of the platform when you say, I've got this property, modeling of equipment to say what properties does it have. But then I've also got this behavior dimension to it all. What behaviors does it all have? And that's where you really end up using both the composability and the inheritance model to kind of get what you need done.
When I
in the Rhize platform, sorry, Dave, the rule engine is associated to classes of things. So we define the rules and the behaviors on classes of things, and so if you model your classes as behaviors, you can then compose a piece of equipment by saying, okay, this piece of equipment has this behavior and that behavior and that behavior. Technically, in the platform, you need to have quite a complicated capability, which is multiple inheritance, which is a well-known sort of computer science problem. But if your platform has that, you can do all this sophisticated stuff.
Yeah, absolutely. Yeah, for me, it's where I was going with this is that it's a data governance issue. It's that the thou shalt versus the that may, and where I look at this conversation is that there are always implications for whatever decision that we're making here, and you really need to think through what does it mean to inherit. What I would call that's the thou shalt piece, versus the composition or the composability of it's the thou may. You can extend this thing out, but you need to at least have these certain core things when you describe it. But after that, hey, use it however you want and whatever it makes sense for that use case. But I think it's important to understand these concepts for sure.
Yeah.
So one of the topics, Geoff, that we've talked about is this concept of event-driven architectures, and it's almost like when we talk about event-driven, whether it be pub sub or there's an event that occurred. I want to make sure we understand exactly what do we mean by that, and there's certain patterns that emerge in this. And there's a gentleman, Martin Fowler. He did a go-to YouTube talk, and we'll link that here below. But he identified there's 4 patterns that are associated with this concept of event driven. Of course, that's event notification, which is the car arrived, or there's the event queried state transfer, which is here's the payload that's associated with it. I'm going to give you here's the information about it, or even event sourcing of where did it come from, and then of course now you get into this CQRS or command query responsibility segregation. There's some concepts that go along with that. Can you walk us through what all these things mean, so that we understand when we're talking event driven, these are the types of things we're looking at?
Yeah. It's and I think we'll put, if we can, we'll put a link into the presentation from Martin Fowler, who's the recognized expert in event-driven architectures generally, into the thread here. But it's a really good topic to explore here. What is an event-driven architecture? Because we talk about it, right? And we say UNS is a platform for an event-driven architecture. What is an event-driven architecture? It's not just publishing based on when something changes. That's a kind of an incredibly simplistic description of event-driven architecture. So what is it? Well, it turns out it's actually this umbrella term that can mean kind of at least 4 different things that we can be talking about. What are these 4 different things? Well, we can be talking about notification of something, and this is the telemetry kind of use case that those of us that have been in sort of SCADA systems and machine control, mostly what we're talking about there is telemetry, which is a notification of something has changed. Right? So it can be as simple as that. As you kind of go from raw telemetry data into kind of more complex events, I've had an over temperature alarm in my car, then it gets more context and there's more state attached to that event. So we can be still talking about a notification there. I've had an over temperature alert in my car, and I can publish just the car's registration plate. It doesn't tell me any context. It just gives me an ID that I can use to go and get the context if I want it. So that's event notification. But there's this other kind of pattern for event-driven architecture, which is event state transfer, event-driven state transfer, where if I wanted another system to be able to fully respond to this over temperature alert in my car, I might need to give it some more information, some more context than just the registration plate of my car. Maybe that's enough, but maybe it needs some more. So how high was the temperature? How long did it stay high for? How many kilometers or miles, depending on which country you're in. Had the car traveled? When was it last serviced? There's all this state, this context of, well, what happened at that point in time, and maybe I want to actually transfer that from one system to another system. So this is kind of event-driven state transfer, which is a different version of event-driven architecture. Now, some people, when they're talking about event-driven architectures, are actually talking about another version, which is event sourcing, which actually means kind of the collection of events over time to build up state. And this is the bank account use case. My bank account, when I look at the balance of it, it shows me a balance, but that balance is calculated based on all the transactions that have occurred. So I've had all these events where I've spent money and received money. Normally it's spent, not so often received. But they're all the events that happen. But how much money have I got in my account? Well, I add up all the events to figure out how much money I've got in the account. This is a pattern of event-driven architecture that's widely used, called event sourcing, where I never really transfer the state. Each system builds up their own view of the state based on the events that have occurred. So I'm transferring events, and each system is kind of figuring it out for themselves. And then there's this fourth different thing, which is event-driven architecture as well, called command query responsibility segregation, which is a bit of a mouthful, which is a whole different architectural pattern for how to do this kind of at scale across distributed systems and separate out the format of the data that might get published in an event from the format that I might want when I'm querying for that data. So allow me, if think about this in a UNS context, it's what I publish might be in a different format, or I might want it to be in a different format when I subscribe to it than when I publish to it. And that's kind of command query responsibility segregation, or CQRS. So event-driven architecture can mean this, simple event notification, the telemetry use case of here's my temperature, here's my speed, or this real-time kind of publishing of current state or notification of telemetry. But it also can mean any one of these other, 3 or 4 quite complex architecture patterns. And the more complex or the bigger the organization, or the more complex the use case that you're looking at, you may need to consider some of these other patterns and ways of doing things.
Yeah, so getting into the event-driven architectures, we tend to use that term very loosely, but there's a lot that goes into it, and I think much like the other topics that we talked about, whether it's composability or choreography, that there's things that are associated with it. So it's important to understand these are all the various things that can, those are the patterns that emerge when we start talking about event-driven architectures and all that's involved in that. So, I think why this is an important topic is just to understand when we say event-driven architecture, what does that mean in terms of what it is that we're trying to build, what's the problem we're trying to solve, and then there's a lot that goes into that. So, any other thoughts that you had on that, Geoff, for event-driven architectures?
Yeah. Yeah, lots. I think about this stuff a lot all the time.
Sure.
One of the questions I get asked quite often, it's two which are related, which is, you're using a graph database. Why didn't you just use like one of the existing ones? We kind of had to go down a path of a very specialized database to make this whole thing work. And why didn't you use Neo4j or one of the other graph databases? And the answer to that is it's too slow, and they generally don't do kind of type safety or schema and ACID compliance, which is a bit of a techie term that just means keeping the data consistent. They don't do those things well at scale, and so when you start to look at these more complex event-driven architecture patterns, it drives very specific requirements into the database. So we use a graph-based database, but it's a very, very specialized graph database to make this all work. The question we get is, well, couldn't you just do this in an SQL database? And we kind of talked about that a little bit and said, well, you can at a small scale, but generally an SQL database will start to struggle at about 12 traversals in a query. So if you've got 12 joins in one query, that's about kind of hitting the maximum of what an SQL query can comfortably handle. And a lot of the queries that we do when we talk about command query responsibility segregation and some of these other event-driven architecture patterns need to be this kind of really wide traversal with sometimes recursive queries in there that mean that's kind of, we hit the limits in there. And then you've got to think about, how do I make this all robust and reliable, and how do I get it all to be high availability, because we're in manufacturing, and you can't just turn a factory off whenever you want to upgrade it and those sorts of things. These event-driven architecture patterns and architectures have the answers built into them for how we deal with all this stuff. So the publishing an event when something changes, that's a good start. But there's so much more. There's so much more that goes in there. And our job as software developers and as community members is to try and kind of deal with all the hard stuff and provide that to people who just want to get on and build applications.
Yeah, absolutely. I mean, that's why we bring it up, because I think this is important, and it's not something you want to overlook.
Thanks for watching or listening to the Rhize Podcast episode 6. In 2 weeks, we'll have episode 7, concluding our conversation with Geoff and Andy. Thanks.